Bismillah Rahman Rahim. So today we would be discussing single degree of freedom forced vibrations and damped system. So as we discussed in the last lecture, we discussed about the equation of motion of the forced damped system. So we developed this equation which is mx double dot plus cx dot plus kx is equal to f naught cos omega t. C is the damping in the system, k is the stiffness of the system, m is the mass of the system, f naught cos omega t is the force of excitation or simply excitation or forcing function, where f naught is the amplitude of the forced excitation and omega is the frequency of excitation. So if we look at the equation, we have a differential equation, second order differential equation, and if you look here on this side of the equation, there is no zero, there is a forcing function. So this is non-homogeneous differential equation. So we have a ordinary second order non-homogeneous differential equation, which is also linear with constant coefficient. Linear in the sense, as we discussed a number of times, that if you look at the x variable, x is the displacement, this is the velocity, and this is the acceleration. If you look at the power of each, the power is 1. So we have a linear differential equation. It is ordinary differential equation because x, which is a displacement, which is a variable, it depends only on t. T is independent variable, where x is the dependent variable. So x, which is a dependent variable, it is only depending upon one independent variable, which is t. So the differential equation that we would get, it would be ordinary differential equation. So we have a non-homogeneous differential equation, and in mathematics you have already studied this, that the general solution of non-homogeneous differential equation would have two parts, homogeneous part and particular solution. But here in vibration we discussed that the homogeneous part would be the transient solution and the particular solution would be the steady state solution. And in case of damped vibration, the transient part, because of the damping, it would be for a specific period of time and then it would decay out. However, the steady state solution, it would stay as long as the forcing function is actually applied on the system and the system is vibrating, so the transient solution would be there. The transient solution is actually the solution of corresponding homogeneous differential equation. So this is a non-homogeneous differential equation. The corresponding homogeneous equation is written here, mx double dot plus cx dot plus kx is equal to 0. And if we look at this equation, this is the equation of motion for natural vibration or free vibration. So it means that when this system, this 1 degree of freedom or single degree of freedom is subjected to a free vibration or natural vibration, then its equation of motion or the dynamic equation would be represented by this ordinary differential equation. And we have already studied this equation and the response of this equation, that is the solution of this equation of motion, could be mathematically modeled as x transient of time is equal to exponential minus zeta omega and t, and in the parentheses we have a cos omega dt plus b sine omega dt, where omega d is the uh, damped natural frequency, the natural frequency of a damped system. Omega d is actually equal to omega n under the root 1 minus zeta square, where zeta is the damping ratio. But that equation, and this response we are expecting when the zeta is less than 1, when the damping ratio of the system is less than 1. So for initially, we have to assume that, let's say if we have an underdamped system, and the zeta is less than 1, then the solution of this differential equation would be represented by this mathematical model. And in this mathematical model, this is the exponential decay, which is actually eating whatever is growing here, or whatever is here, where zeta is the damping ratio, omega n is the undamped natural frequency. And when if we plot this equation, so the plot of this equation would be like this. We would have a vibration, but the amplitude of vibration would be decreasing with the passage of time, depending upon the damping in the system. And after some time, there would be no vibration. The vibration would decay out. So this is the solution of the um, corresponding homogeneous differential equation. So we have this solution. We have already developed this solution. Next, we would be discussing this solution, the steady state solution of the response. So let's assume that the steady state response xss of t is equal to capital X cos omega t minus phi. So we are assuming, because as we discussed, that if the force of excitation is sinusoidal, then we are in the position that we would predict or assume that the response of the system would be also sinusoidal. Uh, so we are actually modeling uh, based on the knowledge that the response of the system would be also sinusoidal. So x is the amplitude of the steady state response, omega is the frequency of the excitation, because we know that in the forced vibration the system would vibrate not at the natural frequency, but it would vibrate at the frequency of excitation. And phi is the initial phase, and this initial phase represents the phase difference between the forcing function and the response, the either lag or lead between those two signals. So, and that phase we are including because of the damping in the system. If there is no damping in the system, then this phase would be zero, and both of the signals would be in phase. That is the But however, here, as we have included the damping in the system, we are discussing a damped system. So we are expecting that the response would actually either lead or lag from the forcing function. So we have to include this phase in our mathematical model. So if this is the solution of the differential equation, then it must satisfy our equation of motion. So for that, I'm differentiating this once with respect to time in order to get the velocity. So the velocity, that is x dot ss of t, is equal to minus omega x sine omega t minus phi, and differentiating this again with respect to time in order to get the mathematical model of the acceleration. So x ss double dot of t is equal to minus omega square x cos omega t minus phi. So putting for x double dot, x dot, and x in our equation of motion for the system. So after doing that, we got this equation. So in the equation, we have cos omega t minus phi, sine omega t minus phi, and again cos omega t minus phi. So using the trigonometric identity, that is cos omega t minus phi is equal to cos omega t cos phi plus sine omega t sine phi, and sine omega t minus phi is equal to sine omega t cos phi minus cos omega t sine phi. Putting this in this equation. So putting for cos omega t minus phi here, sine omega t minus phi here, cos omega t minus phi here. Then in this equation, we would have these terms. We would have these terms. So next, what we would be doing, we are taking common cos omega t, because with some terms we would have cos omega t, and with some terms we would have sin omega t. So taking cos omega t common, so once we take cos omega t common, so in the parentheses we would have all these quantities, that is k x cos phi minus m omega square x cos phi plus c omega capital X sin phi cos omega t. And we have to also take sin omega t common in all those quantities where we have sin omega t. So taking sin omega t common on this side of the equation, we would have k x sin phi minus m omega square x sin phi minus c omega x cos phi and sin omega t is equal to f naught cos omega t. And here there is nothing, that is 0, so I'm writing plus 0 sin omega t. So it is 0, here it is nothing, so I could write this as 0 sin omega t. So on both sides of the equation we have cos omega t, sin omega t, and cos omega t and sin omega t. So on both sides we have cos omega t, sin omega t, so mean, and both sides are actually, mathematics are telling us that both sides are equal. So it means that if these two sides are equal, so whatever here with the cos, it is actually equal to whatever here in the coefficient with this cos omega t is actually equal to the coefficient on this side, the coefficient of cos omega t on this side. Similarly, whatever is here with the coefficient in the coefficient of sin omega t is actually equal to the coefficient of sin omega t on this side. So by equating the coefficients of cos omega t and sin omega t on both sides of the equation, we would get k minus m omega square x cos phi plus c omega x sin phi is equal to f naught, and minus c omega x cos phi plus k minus m omega square x sin phi is equal to 0. So we got two equations. And if we look at these two equations, what what things we want to find? Because if we look back to our equation for the or mathematical model for the steady state solution, so omega is the frequency of excitation. We are actually know we actually know the frequency of excitation, the force of excitation, or we could record this frequency of excitation. So meaning that somehow we would know the frequency of excitation. In order to find the response, if we know omega, then if we know the amplitude of the steady state response and this initial phase for the steady state response, then we would be in the position to know or compute or plot the steady state response. So what we are doing, we are trying to find out the capital X and phi. So now if we look at these two equations, in this equation we have capital X and phi, capital X and phi, and also in this equation we have capital X and phi. The two unknown here are capital X and phi. The two unknown here are capital X and phi. So we have two equations and two unknowns. So in mathematics, if the number of unknowns is equal to the number of equations, then it means that we could solve those two equations for the unknowns. So solving these two equations simultaneously, we would get capital X, which is the amplitude of the steady state response, as f naught k minus m omega square whole square plus c omega square under the root, and the initial phase phi is equal to tan inverse c omega by k minus m omega square. So we got the mathematical model for the amplitude of the steady state response and for the initial phase of the steady state response. If we if we further investigate that whether this phi which we have included in our initial model in the steady state response in order to check that whether it is because of stiffness, mass, or damping. So it is very easy. So here in this equation, you have to just put k is equal to 0. If I put k is equal to 0, k is by putting k is equal to 0 physically, it means that there is no spring or elasticity in the system. So if we do that, so this quantity would become 0, and then in the denominator we have minus m omega square. So phi is not disappearing. It is not disappearing. So what does it mean? That the damping or this phi is not because of this k. If we put m is equal to 0, if we put m is equal to 0 in this mathematical equation, still you could see that in the denominator we would have k. So phi is not disappearing. So it means that the phi is not because of the mass. But if we put c is equal to 0, then 0 by anything is 0. So meaning that this phi is actually because of this damping. This is because of the damping. So because of the damping in the system, there would be there would be the forcing function and the response that would be not in phase, but either there would be a phase shift. There would be a phase shift between these two signals, and that phase shift between the forcing function and the response is represented by this phi. It is represented by this phi. So actually now we have the total response of the system. This is the total response of the system x of t, and this is the transient part. The transient part is exponential minus zeta omega nt a cos omega dt plus b sine omega dt, and then we have the steady state part, which is capital X cos omega t minus phi. So we know that in case of free vibration, the system would vibrate at the damped natural frequency. So here in this mathematical model, you have to include omega d instead of omega. But after some time, actually, when the system is under the influence of the forcing function, then the system would vibrate with the frequency of excitation in the steady state phase. So here in the model, you have to include omega. Capital X, we have already derived the mathematical model for the capital X, that is amplitude of the steady state response and the initial phase of the steady state response. Now here you are looking at the plot of the transient response and the steady state response. So the blue line represents the transient response of the system, and the red sinusoidal plot represents the steady state response. So this is the response of the system uh, uh, in case of free vibration. So mathematics are, and actually if we add these two signals, then this would be the total response. This is x of t. This is x of t. Here both are plotted separately, and here we have the addition of these two signals. So this is the total response of the system. So here you could see that the system has the response, but there is some disturbance in the vibration or signal of the system. And this disturbance is decaying out with the passage of time. And then afterward, we have a stabilized signal. This portion in which actually there is the disturbance, it is known as the transient phase or steady state phase, and whereas this is known as the transient phase or transient state, or this portion is known as the steady state or steady phase. So actually mathematics is telling us that in the beginning, as you start the system and it's if you operate the system and it start vibration, so in the beginning the vibration would be a little bit violent, you could see the amplitude of vibration is too much as compared to the amplitude of vibration in the steady state region. So the mathematics are telling us that in the beginning there would be slight disturbance and the amplitude of vibration would be maximum, and afterward the this disturbance would decrease with the passage of time, and afterward we would have a smooth signal, and when the signal or the vibration is smoothened out, that is known as the steady state response of the system. So mathematics is actually telling us this. So now we have to compare this mathematics with the physics or reality of the system. So what is actually happening in our system? What is the physical interpretation? What the mathematics is actually telling us? So actually, what is happening when we, in reality, when we actually start or the machine? So actually, the machine wants to vibrate at its own natural frequency. The machine wants to vibrate at its own natural frequency. However, the forcing function is there, the force of excitation is there, and the forcing function or excitation is actually pushing the system to vibrate at its frequency, that is the frequency of excitation. So there is, in the beginning, there is a slight fight between the system and the forcing function. The system wants to vibrate at its natural frequency, however, the forcing function is not allowing it to vibrate at its own natural frequency, but rather, rather it is pushing it to vibrate at the frequency of the excitation. And that slight fight is actually going on in this transient phase or transient state. Afterward, afterward, as you see that the this response, that the transient response would be decayed out, there would be no transient response, and then only we would have the steady state response. So remember that the transient phase or transient period would be for a very slight portion of time. Afterward, we would have the steady state response. What is important? Important is that actually, if you look here in the transient phase, the amplitude is very, very large. Amplitude is large as compared to the amplitude to the steady state response. So if you are designing your system, and then you have to include this amplitude in the designing of your system. For example, if you look at the um, jet engines, where we have a rotary compressor, rotary turbine, and we have a row of fixed blades, we have a row of moving blades, and the gap between those blades is in millimeters. So if you are designing that gap for this amplitude, then in the beginning, if you are starting your engine, that is jet engine, so actually it would vibrate, and the amplitude of vibration would be this. Then if you have ignored the transient phase and this amplitude, so what would happen? Actually, the row of moving blades would come in contact with the fixed blades, and then actually there would be that engine would explode like a bomb. There would be a catastrophic failure. So remember that for all those machines where the gaps are critical, then you have to design those gaps while keeping in your mind the amplitudes during the transient phase. In reality, whenever, remember that when we start the machine, whether it is automobile engine, whether it is electric motor, generator, fan, jet engine, or lathe machine, milling machine. So when we are starting the machine, the force of excitation is actually coming from the engine or rotation of the shaft, um, or electric motor. So the machine wants to vibrate at its own natural frequency, whereas the forcing function, actually it is forcing or pushing the system to vibrate at its frequency of excitation. So in the beginning there is a slight um fight between those two, and at the end, after some time, the forcing function is more dominant, and then it push the system to vibrate at its own natural frequency. So after some time we would have a steady state, but before that we would have a transient phase. You have already observed this. If you have not observed this, then try it. In the beginning, if you are start your automobile engine, you would feel that the automobile engine would vibrate a little bit more violently, and this is actually the reason because of the transient phase. Your automobile engine, where the engine is the source of vibration, when you start that engine, that vibration is transmitted through the whole body of the automobile. So your automobile vibrates. So when you start the engine, your automobile want to vibrate at its natural frequency. However, the frequency of excitation which is coming from the engine, it is actually forcing the automobile to vibrate at its own frequency. So in the beginning, we get a little bit violent vibration, and then after a few seconds, you will feel that the more disturbance in the vibration it would be gone, and then the vibration of automobile would be small as compared to the vibration in the beginning. Similarly, whenever we stop our machine, then actually you would feel that as the machine, you stop the machine and everything is coming to rest, my machine would vibrate a little bit violently. Again, the machine would see the transient phase at the end, because at the end, when there is no force of excitation, and the disturbance which was there, the system would start vibrating at its own natural frequency. So at the end, we would have also a transient phase just for few seconds. So we developed the mathematical model for the amplitude of the steady state response in terms of stiffness, mass, damping, amplitude of the forcing function, and frequency of the forcing function. Similarly, we come up with the mathematical model for the initial phase of the steady state response in terms of stiffness, damping, mass, and frequency of excitation. These two equations are not dimensionless. As you see, K, M, and C. So you have to take care of the units, in which units of system you are working. So we would be trying to make this equation the dimensionless, so that we don't care about the system of units. So we know that omega n square, which is the natural frequency of the system, the mathematical model for that is k by m. So we could write this equation as m by k is equal to 1 over omega n square. And similarly, zeta, we know that it is c by cc, that is the actual damping in the system to the critical damping, and it is equal to c, and the critical damping is 2m omega n. So from there, that is c by 2m omega n. If we bring this quantity on this side of the equation, the actual damping of the system would be 2m zeta omega n. So we have these two equations. So if we uh, take this k common, so I'm writing this k here. If we take this k common, so there is square here. So if I'm taking k common, so actually I'm taking k square common here. So k square, I have to write k square here. So k square here, and this would become 1, and this would become m by k. This quantity would become m by k. And similarly, I'm taking k common here. So square is, if you look here, here we have square, so k square would come here. So k square here, and this would become c by k. So what we did, I took k common from here, so this become 1 n by k, and out of the parentheses we would have k square, k square. So I can now take this k square and this k square common. So this is under root. So outside we would have what? We would have k. So outside, what I'm doing, I'm writing k here. So k is here, and this is m by k, and this is c by k. So m by k is actually 1 over omega n square. So meaning that this m by k is 1 over omega n square. So we could, and here we have c by k. So here we have already discussed that c is equal to 2m omega and theta omega n. So dividing this equation on both sides like this. So when I divide this on both sides, so c by k is equal to 2m by k zeta omega n, and m by k is actually equal to 1 over omega n square. So for this m by k, I could write down 1 over omega n square, which is here. So this omega n square, omega n would cancel with 1 omega n. So at the end we would have c by k is equal to 2 zeta 1 over omega n. So instead of c by k, I am putting 2 zeta 1 over omega n, and instead of m by k, I am putting 1 over omega n squared. So after doing that, once I put omega n instead of m by k, which is 1 over omega n square, I would have omega by omega n whole square, and then whole square plus 2 zeta omega by omega n whole square. And here I have k. So we could, I'm bringing that k on this side of the equation. So the quantity here would be capital X k. And here we have f naught, so I'm bringing that f naught on this side of the equation. On this side of the equation. So I have x k f naught is equal to 1 over 1 minus omega by omega n whole square, and square plus 2 zeta omega n by omega n square under zero. And if we look at the phase, in the phase what I'm doing, I'm taking this k common. So if I take k common, so this k is here, so this would become 1, and here I would have m by k. I have taken k common, and I have 1, and I would have m by k. And m by k is 1 over omega n square. So this is this quantity. So in this k, I am writing this k here with c, then I would have c by k. I would have c by k, and c by k is what? C by k is 2 zeta 1 over omega n. So here I could write this for c by k, and this for n by k. So after writing this, then we would have so after replacing for c by k in the numerator and m by k in the denominator, then the phase would be 2 zeta omega by omega n 1 minus omega by omega n whole square. Now if you look at the equation, omega by omega n, it is the ratio of frequencies, and it is known as frequency ratio, where omega is the frequency of excitation and omega n is the natural frequency of the system. Here again you see the frequency ratio, and zeta is also the ratio. So this has no unit, this has no unit. So this side of the equation is completely unitless. It has no unit. If you look at the other side of the equation, this is the displacement and this is the stiffness. Stiffness times displacement is force. It is force. F is equal to kx. So this is the force. So it would have the unit of force. And here again we have the amplitude of the force. It has the unit of the force. So it is actually somehow the ratio of the forces here. So it is again has no unit. So this side is unitless and also this side is unitless. So we come up with the dimensionless equation. This is a dimensionless equation. So this is actually known as the magnification. This is known as the magnification. This is the frequency ratio and this is the damping ratio. So now if you look here, this amplitude of the steady state response only depends upon what? It depends upon the frequency ratio and damping ratio. So for frequency ratio and damping ratio, we could actually simulate or plot this mathematical model. Similarly here, if you look at the numerator of the initial phase, so we have a frequency ratio, no unit, and damping ratio, no unit. Again here, frequency ratio, no unit. So the initial phase is also a dimensionless equation. So what we have done, we have actually transformed a dimension equation, which depends actually on the system of units, into a dimensionless equation. Now we could actually simulate these two mathematical models, because these mathematical models actually depend upon two parameters, which is the frequency ratio and damping ratio. So let's simulate these two equations. So simulating the first equation, what we are doing, we have to change the frequency ratio and the damping ratio, and we have to find this magnification. So we are taking the magnification, this magnification we have to take along the vertical, and I'm taking the frequency ratio along the horizontal. So the frequency ratio I'm taking along the horizontal, so frequency ratio omega by omega n, and the magnification, which is xk by f naught, we are taking this along the vertical. The magnification actually represents the amplitude of the steady state response, and this is our mathematical model which we have just developed. And we are plotting this, we are doing this for different values of zeta, different values of zeta. Zeta is the damping ratio, and the range for this damping ratio, the range for damping ratio is from 0 to infinity. Zeta is C by Cc. So C, what is the range for C? The range for the damping in the system is from 0 to infinity. I will write down this here. The range for C is actually from 0 to infinity. So zeta, which is C by Cc, so its range is actually also from 0 to infinity. What we mean from 0? 0 means no damping. Infinity means too much damping. So the range for the actual damping in the system could be, theoretically it could be from 0 to infinity. So as you range C from 0 to infinity, so zeta could be from 0 to infinity. But we would be not actually simulating it up to infinity, but we have to simulate it from the lower values or small values of zeta to large values of zeta, and then we would look at the magnification or response of the system. So along horizontal axis, frequency ratio, vertical magnification, and we are plotting for different values of zeta. So here you have seen these numbers, and these numbers represents the value of zeta. For this red line, zeta is 0.05, 0.15, 0.2, 0.3, 0.4, 0.5, 0.6, 0.8. So these zeta values are less than 1, meaning that these damping ratios, in these damping ratios we have underdamped system. And here you see in this pink line, zeta is 1. So this is actually the zeta, that is zeta is equal to 1. So it is for critical system, a critically damped system. So this is for the critically damped system, and here you see that zeta is more than 1. So this is for our damped system. So we have plotted uh, the response of underdamped systems, which actually range from zero point 0.8 to 0.05. You could see also the response of the critically damped system and our damped system. So for different values of zeta, we have simulated the dimensionless equation for the magnification or the amplitude of the steady state response. Now, after simulation, you are seeing these plots. Next is actually we have to interpret. We have to analyze these simulation and interpret. So one, frequency ratio one, what does frequency ratio one means? Frequency ratio one means that when omega is equal to omega n. When the frequency of excitation is equal to the natural frequency of the system, it means resonance. So this one, frequency ratio one, means resonance. It means that at this instant, the frequency of excitation matches the natural frequency. And you could see that at this instant, when the frequency of excitation is matching the natural frequency of the system, we see uh, more magnification, higher value of magnification for the underdamped system. So what is the physical interpretation? If you look here, if the damping ratio is less or the damping in the system is less, we see more magnification, more amplitude of the steady state response. So if we are increasing the damping ratio or damping in the system, then the amplitude of vibration at the resonance has decreased. You can easily see that when we have increased the damping in the system, then the amplitude of vibration at the resonance has increased, has decreased, sorry, has decreased. So meaning that physically, if you want, if you have a system and your system is vibrating violently at the resonance, and you want to decrease the level of vibration or amplitude of vibration at the resonance, so what you have to do, you have to increase damping in the system. In other words, the damping in the system would control the amplitude of your system at the resonance. So clearly you could see that when the damping in the system or damping ratio, damping in the system is increased, so the amplitude of vibration at the resonance would decrease. Similarly, here this is the magnification one, magnification one. So if we look here, we could divide this simulation into a number of regions. This is frequency ratio 1. So this is the region where the frequency of excitation is less than the natural frequency. And this is the region where the frequency of excitation is more than the natural frequency of the system. If you look here, all these lines are converging. All these lines are converging, meaning that at higher frequency ratios, the magnification would have a lower value, and at much higher frequency ratios, the magnification or the amplitude of steady state response would be approximately zero, meaning that at very high frequency ratios, the vibrations would be very, very small. It would be not zero, but very, very, very small. However, as you move in the reverse direction, as you move towards the resonance, and if your system is underdamped, then we are expecting that the magnification would have a large value, or the amplitude of the steady state response would have a large value. Depending upon what? Depending upon the damping ratio, or depending upon the actual damping in the system. If the also if you look here, the region where the frequency ratio is less than 1, or the frequency of excitation is less than the frequency natural frequency of the system, then all these lines are converging where the magnification is 1, where the magnification is 1. Magnification 1 means that in this case actually, I will write the equation down here. If you look at this magnification, we have write x k is equal xk by f naught is, I could also write this as x by f naught by k, where f naught by k is what? F naught by k is the static deflection. So x by static deflection, it is static deflection, st, static deflection. So x by static deflection. And if this is equal to 1, so what does that mean? It means that capital X would be equal to static deflection, delta S2. So meaning that it means that at much lower values of frequency ratios, or at lower values of frequency of excitation, we are expecting that the amplitude of the steady state response would be near to the static deflection, which is f naught by k. They all are converging. So this we could see for the all underdamped values, and also for this critical damped system, and also for this overdamped system. So the overdamped system response, you could see the response of the overdamped system. So here near the when the natural frequency ratio is very near to 0, it would have a value which is actually equal to the static deflection. Afterward, at higher values of frequency ratios, the amplitude of vibration would be very, very less. Similarly, that here all this. Similarly, we could plot the initial phase for the steady state response. This is the mathematical model that we have developed for the initial phase, 2 zeta omega by omega n by 1 minus omega by omega n. So we are taking the frequency response along the horizontal, whereas the phase angle, that is phi in radians, along the vertical axis. Here the phase is in pi, here it is in radians, uh, in degrees. So here you could see again, we could divide this into two regions. This is the region where the frequency ratio is less than 1. Frequency ratio 1 means resonance, and this is the region where the frequency ratio is more than 1. So you could see the simulation. One important point is here, irrespective of the damping, these values or these plots are for different values of damping ratio. This is for our damped system. This is for critical damped system. This is for damping ratio 0.4, 0.2, 0.15, and the red one is for 0.05. So irrespective of the damping in the system, irrespective of the damping ratio, all these lines are actually converging on this point. And if you look here, this point is at the frequency ratio 1, which means that at resonance. It means that irrespective of the damping ratios or damping in the system, at resonance, what would be the initial phase? The initial phase or the phase angle would be pi by 2. pi by 2, 90 degree. So 90 degree would be the phase angle for the response of the system at the resonance, irrespective of the damping. At lower at lower frequencies ratios, the phase angle, the initial phase or the phase angle would be less than 1. It would be less than what? It would be less than 90 degrees. Here you could clearly see that this is the line for the 90 degrees. So at the frequencies ratios less than 1, the phase angle is less than 90 degree. Whereas for the frequency ratio more than 1, you could see that all these lines are in this region where uh, the phase angle is more than 90 degrees. So when the frequency ratio is more than the is greater than 1, then the phase angle would be more than 90 degrees. And here depending upon the damping, if the damping is less, you could see that at higher frequencies ratios, if the damping ratio is less, then the phase angle would be approximately 180 degree. It would be 180 degree. What does that mean? It means that both the signals would be out of phase. Both the signals would be out of phase. Both signals, what I mean, the forcing function and the steady state response. Also, this is the same plot for the magnification. Same plot for the magnification, and also for the phase angle. Similarly, we could also look at this equation. In this equation, if we put omega by omega n is equal to 1, omega by omega n is equal to 1 means resonance. The frequency of excitation is equal to the natural frequency of the system. So this quantity would become 1. So 1 minus 1 is 0. So this quantity would become 0. And if you look here, so omega by omega n is 1, and then we would have 2 zeta whole square under the root. And after applying the under root, because we have 2 zeta square, the equation for the magnification would become, it would become 1 over 2 zeta. So at resonance, the magnification, it means that at resonance, the magnification only depends upon what? It depends upon zeta. So in order to decrease this magnification, you have to actually increase what? You have to increase zeta, because zeta is in denominator. So if we increase zeta, that is the damping in the system, then the magnification at resonance would decrease. So that is a very important actually conclusion from the model or simulation. If we take no damping in the system, if I put this 0, 0 means no damping in the system, then we would have what model says to us, that it would be 1 over 0, and 1 over 0 is actually infinity. Then in case of no damping, that is underdamped system, undamped system, in case of undamped system, the magnification would become infinity. Capital X would become infinity. So this actually mathematical model is telling us. So the mathematical model is telling us that in that case, your amplitude of the steady state response would become infinity. In reality, infinity means that x infinity means that your mass is actually moving, and it is moving, and it is going into the sky, and it would reach one end of the universe, and from there it would again come back and pass to the equilibrium position, and it would reach the other end of the universe. This is not happening. If we come to the reality, this is actually not happening. So what is actually the reason that the model is telling us the infinity? More of the students are just thinking that at resonance, the amplitude of the vibration would become infinity and our system would destroy. This would not happen in reality. Actually, the model is not so sophisticated. The model which we have developed, this model is not so sophisticated, and it is not capable to calculate the exact value at the resonance for underdamped system. It it is actually giving us the exact values, accurate values, approximately accurate values at all other values of frequency ratios and damping ratios. However, for this particular case where frequency ratio is 1 and zeta is equal to 0, it is not capable to calculate the accurate value for the magnification or for the amplitude of the steady state response. Just it actually reflects a value that at under this condition, when zeta is equal to 0, frequency ratio is 1, that is at resonance, the magnification would be large, but I am not in the position to calculate the value for you. So the problem is in the model. The model is actually not capable to give you the exact value at resonance when the damping ratio is 0. So the problem is in actually in the model. But in reality, we know that if even the damping in the system is 0, the system would vibrate violently, but there would be a certain value for the or specific value for the steady state response, that is capital X. Although the chances of failure at such violent vibration or for the system components it would increase, but it doesn't mean that under that condition the system would explode into pieces.